Alright, so now we're going to start getting into our trig portion of this class. And this part is going to be a little bit of review, and then we're going to be adding some new stuff too. So we're going to look at the Pythagorean theorem just to go back over it, because I'm sure you've already done that. We're going to look at some special right triangles and what they tell us. We're going to look at, and also in that, we're going to pretty much be simplifying some radicals, so that's some review too. Then we're going to look at trig functions and like sine, cosine, tangent, stuff like that. And then we're going to look at some trig ratios with special angles. So this won't be too difficult, I don't think, but we're going to look at it anyway. So first thing to get into, the Pythagorean theorem, hopefully we all know this, is a squared plus b squared equals c squared. So we have a little triangle over here that just is looking at that. So when we're looking for the hypotenuse, which is c, then we say a squared plus b squared equals c squared. We just have to remember that c squared equal to something isn't our answer. We have to take the square root of both sides to get it. But we can also, if we have like a or b or a leg left out, we can figure that out too by using a squared plus b squared equals c squared. So if we look at an example of this, like on number 1, we've got 4 and 8. Those are our legs of our triangle. And then our hypotenuse is always this long leg here. And for some reason, it doesn't want to work. Okay, there it goes. So what we're going to do is we're going to take a squared plus b squared, which, I mean, to be honest, it doesn't really matter which one you use as a squared or b squared, but I'm going to use 4 as my a. So I'm going to have a squared equal to 16. And then I'm going to use 8 as b. So then b squared is going to be equal to 64. So then make sure you've got that written down. So then I'll have a squared, which is 16, plus 64, equal to c squared, or we could call that like x squared. So you can make this c squared, as long as you have it as a variable, it doesn't matter, or you could have this as x squared, it really doesn't matter. Since here it's x, that's why we can use x squared, but it doesn't really matter, like I said. So let's see, 16 plus 64 is 80. So we're going to have 80 is equal to x squared. You just have to remember, anytime you have something like this where we have an exponent with this variable, then we're going to have to take the square root of both sides to get rid of it. So that's going to give me x is equal to the square root of 80. Then, if I want to reduce this, I'm just going to have to reduce this radical. So we need two numbers that will still give me, that'll be multiplied to give me 80, and I need my greatest common factor that's a perfect square. So for this, I could use 16 and 5. So 16 times 5 is 80, and then this square root of 16 is going to give me 4 on the outside. So I'll have x is equal to 4 times the square root of 5, or 4 radical 5. And then the only difference between this and number 2 is now number 2, that it leaves out a leg. So I'll go ahead and do that one with you real quick just so you can see it. But the only thing that changes here is they leave out a leg. So let me look at that one. All right. So now x here, or the side that's left out, is a leg instead of this hypotenuse. So this hypotenuse, which is the long, like diagonal looking leg, that's going to be c squared. So if we set this up, we're going to have c squared is equal to a squared plus b squared. And now we're given 24 as c, so we'll have to take 24 squared equal to, it doesn't really matter if you use 22 as a or b, it doesn't really matter. I think technically it's b, so this would be x squared or a squared plus 22 squared, because that is b squared. So then once we get those values, we'll be able to solve this, which is not too bad. So 24 squared is going to give me 576. Let me zoom in a little bit so I can write better. Okay, so 576 equal to x squared plus, what would that be, 484. So then all I have to do here is subtract 484 from both sides. I'm essentially solving for x squared to begin with, so I'm just going to move this to the other side. That'll cancel out. And then 576 minus 484 is 92. So now I've got 92 is equal to x squared. So now the only thing I've got to do here is just remember that x squared can't be my answer. I need to take the square root of both sides to get what x is equal to. So x is going to be equal to the square root of 92. Now 92 is a weird one, but if we want to break this down further, we can take two variables. Let's see. We would use 4 and 23, I believe. Let me check and be sure. I think that's right, though. 23 times 4. Yeah. So we can use 4 times 23. And now I can take the square root of this 4. So x is going to equal 2 on the outside, radical 23. So that's your review for the Pythagorean theorem. You're going to have to do this in some of the steps we do, but that's the first part of this section. It's the Pythagorean theorem. Now we're going to get into special right triangles. So when we have a 45, 45, 90, which just means, as you can see here, we've got a 45-degree angle, 45-degree angle, and then that gives us a 90-degree angle. So when you have a 45, 45, 90 triangle, each of your legs are both x, meaning that they're the same number. And then your hypotenuse is x radical 2. And you'll see how we use these in a second. So this is something you're going to need to know. So a special right triangle of 45, 45, 90, the two legs are both x, and then the hypotenuse is x. The hypotenuse is x times radical 2, or x radical 2. Then we've got one more, a 30, 60, 90. So that's when you have a 30 degree angle on one of your sides, and then a 60-degree angle, and then a 90-degree angle. So the shorter leg, which is going to be here, that is going to be x. Your longer leg, which is your longer leg, is going to be x radical 3. And then your hypotenuse, which is the diagonal leg, is going to be, I think it is 2x. Yeah, 2x. So that's all the information you need to know for these, and I'll show you how we'll use those to figure out what our legs are, or what our hypotenuse is. We can use this for what we'll do next. So make sure you get this stuff written down. Now we'll look at some examples. So like on number 3, first you need to identify what you're actually looking for. So if we're looking at x here, x is a leg, and since this is a 45-degree angle, that means we've got a 45, 45, 90. So that means x here is going to be our leg, which in our like in our definitions, our legs are equal to each other. So if our other leg here is 10, that means x is also going to be equal to 10. So when you're given a problem like that, it's pretty easy. Now what we need to know, though, is y, which is the hypotenuse in this case, because both of these would be our legs, and then our diagonal line here would be our hypotenuse. Which a good way to remember this, since we're looking at right triangles, the hypotenuse is always going to be opposite of the right angle. So like this is our right angle here. Opposite of that is our hypotenuse. So if we go and look back at other problems, like if we look back at the original triangle, our 90-degree angle's here, so our hypotenuse is opposite of that. Just like in number 2, our hypotenuse was opposite of this 90-degree angle. So that's a good way to not get confused of where your hypotenuse is. So if our hypotenuse that we're looking at is the hypotenuse of a 45, 45, 90. That means that if x is equal to 10, our hypotenuse is going to be 10 radical 2 because our hypotenuse is just x radical 2. So in this case, we already know what one of our legs is, so we're just going to take that leg and then add radical 2 with it. And so our x here would be 10, which is our leg, and then our y here would be our hypotenuse. That would be 10 radical 2. So that one's a pretty easy one. Number 4, though, gets a little bit trickier. So on number 4, if we identify what we have, if we go to the opposite of our right angle, you'll see that we have our hypotenuse here is 16. So what we're actually looking for is both of these legs. If we can find one leg, that gives us both legs, because if we go back, both of them are equal. They're both x. But we need to figure out what that x is. So here's what you do. We're going to take 16 and set that equal to what our hypotenuse should be equal to, like in our general definition form. So our hypotenuse should be equal to x square root of 2. So we're going to take 16 and set it equal to x square root of 2. Now this is where things get a little weird, because this is also a little bit of a review. So I'm going to come over here and do number 4, or finish it. So right now we've got 16 equal to x square root of 2. So we've got to solve this. Now to solve this, we need to get x by itself. Anytime we have x multiplied by a number or whatever it is, to get rid of it, we do the opposite. So here we would be multiplying, so now we would divide to get rid of it. So we would end up with x is equal to 16 over square root of 2. Now, that is all fine, except we can never have a radical on the bottom. So this should be review, but I'm not sure how much you remember of it, but we're going to go back over it now. So if you ever get a square root or a radical on the bottom of a fraction, you can't do that. But what you can do is, it's basically like a little trick you learn. You just do this, and it pretty much accounts for it. So anytime you have a radical on the bottom, what you do is you multiply the top and bottom of your fraction by whatever that radical is. So we have a radical 2, so we're going to multiply 16 by radical 2 and radical 2 by radical 2. And we'll end up getting x is equal to 16 radical 2 over, now, if we take radical 2 times radical 2, that's going to give us radical 4, which the square root of 4 is 2. So that's just going to give us 2 on the bottom of our fraction. Now we no longer have that radical on the bottom. All we have to do here now is divide this portion, 16 over 2. So x is going to be equal to 8 radical 2. So if x is equal to 8 radical 2, that means that our legs, both of them, since this is a 45, 45, 90 triangle, both x and y here, which is our legs, are going to be 8 radical 2. Let's see. I'll work number 5 again. Make sure you get this written down over here, number 4, the work for it, because it's, I don't know, that can be a little bit confusing, so you may have to go back over it. We'll look at another problem for a 45, 45, 90. So on number 5, this one's a bit easier, but I'll show you the steps for it anyway. So on number 5, we've got a 45, 45, 90 triangle. And that means that if we know basically our two legs, if that's what we're looking for, those are going to be the same. And then the hypotenuse is going to be equal to x radical 2, which is just up here. So if we go and look at this, it leaves out x and y here, which those are our legs. But if we didn't know those were our legs, we could identify our 90-degree angle and go across or opposite from that. And that line is going to be our hypotenuse. So our hypotenuse is 14 radical 2. So we're going to take the same step as number 4, except this time it's going to be a little bit easier. So if we look at this, if we have 14 radical 2, and it's our hypotenuse, it should be equal to x square root of 2. So we're going to set that equal to x square root of 2. Now you'll see when we divide here, something pretty good happens for us. So if we divide both sides by radical 2 to get x by itself, both those radical 2's cancel out, so we're left with 14 is equal to x. And that is actually the length of both our y and our x, which are just our legs, because those are the same in a 45, 45, 90 triangle. So a problem like that actually works out good for us because it made life pretty easy on us. We didn't have to rationalize anything. All right, so now let's look at 30, 60, 90. So just to review, when we have a 30, 60, 90, our shorter leg's going to be x, longer leg is x radical 3, and the hypotenuse is 2x. And those, you can pretty much tell which one's longer than the other just by looking at it. But if you didn't know that, the leg that is adjacent to the 30-degree angle, that one's going to be longer than the leg that is adjacent to the 60-degree angle. So if we go to number 6, we are given a 30-degree angle, so that's just an indicator we have a 30, 60, 90 triangle. Now we need to figure out, what are we looking for? Are we looking for legs, hypotenuse? What are we looking for? So if we want to figure that out, just go to your 90-degree angle, or if you want to test if you're given the hypotenuse, go to your 90-degree angle, go opposite of that, and that's your hypotenuse. So we're given our hypotenuse, which is 8. Now, we can do the same process as we did with 4 and 5. If we want to know what our hypotenuse is, or what x is from our hypotenuse, 8 should be equal to 2x, which is the hypotenuse for our 30, 60, 90 triangle. So we're going to take our hypotenuse and set that equal to 2x. Then we'll be able to plug in x into our definitions for our legs, and we'll be able to figure those out. So if we do this, we'll divide by 2 on both sides, so we'll get x is equal to 4. Now that doesn't necessarily mean this x equals 4. That just means when we're looking at, back at our definition here for our shorter leg, longer leg, and hypotenuse, that means x there is equal to 4. So now we need to identify our shorter leg and our longer leg. So our shorter leg is going to be here. That's what x is. And then our longer leg is going to be here. That's what y is. So for x, that's our shorter leg. If we go back up, our shorter leg is just equal to x. So if x is 4, that means our shorter leg is 4. So in this case, it just happened to work out that way, where it was equal to what you found, but that may not always be the case. Now, our longer leg, which is y here, is going to be x radical 3. So all we have to do here, we already know that x is equal to 4. All we have to do here is say 4 radical 3. And then that would be your answer. So in number 6, they left out our legs and gave us our hypotenuse. Now we'll go to 7. And here we're given one leg, but we're not given our hypotenuse, which we know that because it's opposite of the 90-degree angle. So this x is our hypotenuse. And then this y down here is one of our legs, and we can just identify if it's shorter or longer, which it's adjacent to the 60-degree angle, so it's shorter. But, I mean, you can look at them and just see that the bottom one's longer than the top one. So this 27 we're given is our longer leg. So our longer leg, if we go back to like our definitions, our longer leg should be equal to x radical 3. So we're going to have to set 27 equal to x radical 3 to figure out what x is equal to. So I'll do this again. We're going to end up having to rationalize something, so I'll do this over here again just so you can see it. So number 7, we are to 27 is equal to x radical 3. So now we're going to have to divide both sides by radical 3 to get x by itself. Now that's going to give us a problem here. So on the right side, it works out nicely. It just gives us x. And then we're going to be left with 27 over radical 3. Now here's where we have our little speed bump, because we can't have a radical on the bottom of a fraction. So we're going to have to rationalize this, which just means we're going to multiply the top and bottom by radical 3. And then that's going to take care of our problem, because we're going to have x is equal to 27 radical 3. And then on the bottom, if we take radical 3 times radical 3, that's going to give us radical 9. And the square root of 9 is 3. So now we no longer have a radical on the bottom. We just have to divide 27 over 3, which is going to give us 9. So we'll have x is equal to 9 radical 3. Now, that does not necessarily mean that x here is equal to 9 radical 3. It means when we go back to our 30, 60, 90 like definition for each part, it just means that x for our shorter leg is, or x in general, is equal to 9 radical 3. So actually we were left, our shorter leg is actually y here. So x is going to be equal to that shorter leg pretty much. So that one's pretty easy to do. It's just 9 radical 3. Now the harder one is the hypotenuse. The hypotenuse should be equal to 2x. So that means we're going to take 2 times x. So we're going to take 2 times x, which x here is 9 radical 3. So we're going to say 2 times 9 radical 3, which is going to give us 18 radical 3. So that one's not too bad either. All right, so then the last one, we've got 8. Number 8 leaves out our hypotenuse and our longer leg, which if we want to know if our hypotenuse was left out, identify your 90-degree angle, go across from it, that's our hypotenuse. So x is our hypotenuse. And then we're given a 60-degree angle here, so we know this is a 30, 60, 90 triangle. And the leg or the measurement that goes with that 60-degree angle or that's adjacent to it, that's going to be our shorter leg. So this 5 radical 6 is our shorter leg, so y is going to be our longer leg. So if our shorter leg is 5 radical 6, that means that in our general form, or like in our definitions, x is equal to 5 radical 6. So we don't really have to do any calculations with that. So we know x equals 5 radical 6. Not this x, but our x just in general. So then we can take that, and to find x and y, pretty much for the hypotenuse, it's just 2x. So 2 times 5 radical 6 will give us our hypotenuse, because that's our general setup that we have for the hypotenuse. So 2 times 5 radical 6 will just be 10 radical 6, and then we're done. And then let's see, the last one is y. So for y, we end up saying x times radical 3. So here is a little bit different, or it may look a little weird, but it's not too bad. Essentially here what we're doing is saying 5 radical 6, which is x in our general form, not x here, times radical 3. So when we multiply those two, we'll end up getting, let's see, I'll move it over here. No, I probably can do it. So we'll end up with 5 square root of 18, because we just multiply our numbers in our radical and keep it under a radical. So we'll end up with 5 square root of 19. Then we just have to simplify this. So that's going to be equal to 5 times 9, or let's see, equal to 5 radical 9 times 2. So we can take out the square root of 9, which is 3. So now we'll have 5 times 3 radical 2, which is 15 radical 2. So it's not too bad, but that part can be a little tricky. All right, so those are our 45, 45, 90 triangle calculations and our 30, 60, 90 calculations. And really, it's dealing with some radicals and stuff, but it's not too bad once you get used to it. All right, so now let's look at our trig functions. So our trig functions, basically they're a ratio, and what I would tell you to do is remember this. Remember SOHCAHTOA. If you remember SOHCAHTOA, you will remember all of these, I promise. Because here's what happens. When we make sine, cosine, and tangent, we just use SOHCAHTOA to do it pretty much. But before we do that, the Greek letter that's used to represent the angle is going to be this. It's going to be like a circle or a 0 with like a line through it, and that is theta, which I'll just write it out for you. So we say that as theta. So if you see that, that angle is theta. All right. So now, if we have a a triangle like we see over here where we've got A, B, C, and then theta is the measure of this angle, which I guess it would be this angle here. It's the measure of that angle. So if we want to use that angle, we can use SOHCAHTOA to figure out all of these. So for sine, which is what SO stands for in this, O stands for opposite. So for sine, we say opposite over, and H stands for hypotenuse. So we say opposite over hypotenuse. And if we look at this triangle over here, that just means that we start from our theta, our angle, and we go opposite, which that would be A. And then the hypotenuse here would be C. So if we were just looking at this, we would say A over C, which is opposite over hypotenuse. And that's what the SO stands for in SOHCAHTOA. Now, same thing with cosine. So cosine is this second piece here, which is ca, I guess. So it's CAH. So that means cosine is adjacent. That's what A stands for, over hypotenuse. So cosine is adjacent over hypotenuse. And then if we look at our triangle again, that just means that our adjacent angle to our adjacent leg or side to this angle here is the one that's just directly beside it. Basically, it's the one that's not opposite. So if you go to the opposite, it's the one that's not opposite and not the hypotenuse. So that would be B here, and then our hypotenuse is still C. So this would actually be B over C if we wanted to look at it that way. And then tangent is a little bit different. That's where the TOA comes in. Tangent is opposite, which is the O here, over adjacent, which is the A here. So now we leave out the hypotenuse and we do opposite over adjacent. So if we have this angle theta again, the opposite would be A over the adjacent would be B, so it would be A over B. Now, the easy part next is when we look at the reciprocal functions. So cosecant is the reciprocal of sine. So if sine is opposite over hypotenuse, then cosecant is just hypotenuse over opposite. So everything just flips. That's why I said if you know SOHCAHTOA, you can figure out cosecant, secant, and cotangent because you just flip whatever sine, cosine, and tangent is. So secant goes with cosine. So secant is pretty much the reciprocal of cosine. So if cosine is adjacent over hypotenuse, secant is hypotenuse over adjacent. And then cotangent is the opposite, or it's the reciprocal of tangent. So cotangent is adjacent over opposite. Pretty much once you find sine, cosine, tangent, you flip sine to get cosecant, you flip cosine to get secant, and tangent to get cotangent. Now we're going to look at some examples with this. So if we look at the first problem, we're given a right triangle here, and we're given an angle here, theta, so we can use that to figure out our 6 trig ratios. Now, if you notice here, the only problem we'll run into is we don't know what this hypotenuse is, which if we want to make sure it's the hypotenuse, find the 90-degree angle, and then go opposite of that, and that's our hypotenuse. So in order to find that hypotenuse, we're going to have to say 30 squared, which is a squared, plus 16 squared, which is b squared, is equal to c squared. So pretty much we're going to have to use the Pythagorean theorem here to figure out what that hypotenuse is. So what you'll end up with is 900 plus 256 equal to c squared. So then c squared is going to be equal to 1,156, and then we've got to take the square root of both sides. So if we take the square roots of both sides, we will get, c equals 34. So that just means that our hypotenuse here is 34. So now we're good to go. Now all we've got to do is use SOHCAHTOA, and we can figure out sine, cosine, tangent, and then we can just flip those and get cosecant, secant, and cotangent. So let's do that now. So sine is going to be opposite over hypotenuse. So if we go to theta and we go opposite of that, that's going to be 16. And then our hypotenuse is 34. And then we just have to reduce that fraction, which it reduces down to 8 over 17. Then we have cosine, which is adjacent over hypotenuse. So if we want to go to our triangle, go back to theta, whichever angle wasn't the opposite of theta and wasn't the hypotenuse, that's going to be the adjacent angle, or pretty much it's connected to this angle here. It's connected to where this angle ends up meeting. So then we're going to get, let's see, that would be adjacent over hypotenuse. So that would be 30 would be the adjacent over 34 is the hypotenuse, which is going to reduce down to 15 over 17. And then last, we've got tangent, which is opposite. So that would be 16 over adjacent, which would be 30. So 16 over 30 is going to reduce down to 8 over 15. And then the cool thing about these, or I guess the easy thing here, is that if we want to know what cosecant is, we just take 8 over 17 and flip it. So now we'll have 17 over 8. For secant, we just take cosine, which was 15 over 17, and flip it. And then for the last one, we take tangent. For cotangent, we take 8 over 15 and just flip it. So we'll get 15 over 8. And that is how you use your right triangle to figure all of those out. Now I think, let's see. I'm trying to make this video as short as I can, but it may just have to be long. Whatever, that's fine. We can deal with it. All right. So now we'll look at number 10 too, because number 10 is a little tricky. All right, so on number 10, we're given a ratio for cosine. So we're given what cosine is. We're given that cosine is equal to 2 over 3. We can use that and make a triangle, and then we can figure out the rest of these. Here's how you do it. So you'll set up a triangle, and that triangle will pretty much look similar to this one here. It'll look pretty much similar to this. So what we're given here is cosine. So we're going to use what we know about cosine. We know that cosine is adjacent over hypotenuse. So that means if we have an angle, which the safe bet's to always put it in the bottom right corner. So if we have this angle theta, that means that the adjacent side is going to be 2, which would be, this is a right triangle. This would be 2. This would be the side adjacent to theta. And then our hypotenuse would be equal to 3. So the only thing here we don't know is this other leg that we have. So we have to figure that out. But we can do that because we can just use a squared plus b squared equals c squared, and we can figure that out. So if we do that, we'll say a squared plus b squared, which would be 2 squared, equal to 3 squared. That would give us a squared plus 4 equals 9. We would subtract, I don't know why I said subtract 5 when we're subtracting 4. So we're going to get a squared is equal to 5. So that means that a is going to be equal to the square root of 5, because we've got to take the square root of both of these, which will give us a. So the square root of 5 is equal to a, which is what this is equal to. So our leg here is 5. This is where things get a little tricky, because you'll have to rationalize this. So this is where things get a little tricky, but we'll do it. All right. So for sine, we're going to take the opposite over the the opposite over the hypotenuse. So the opposite here would be the square root of 5 over 3, because that's our hypotenuse. For tangent, we're going to take the adjacent or the opposite over the adjacent. So we're going to take square root of 5 over 2. So square root of 5 over 2. Now for each of these, we just have to flip sine, cosine, and tangents for the rest of these. So this is where things get a little tricky, because once we take the square root of 5 over 3 and flip it, we end up with 3 over the square root of 5, which we can't have that. So we're going to have to multiply the top and bottom by 5. And then that's going to give us 3 square root of 5 over 5, and that is cosecant. So that's where things get a little weird when you have a radical on the bottom, but we can deal with it. For secant, it's pretty easy. We just flip cosine, which is 2 over 3, so we'll get 3 over 2. That one's pretty easy. And then cotangent's kind of like cosecant. We've got to flip square root of 5 over 2, which is going to give us 2 over square root of 5, which we can't have that radical on the bottom. So we take 5 or square root of 5, multiply it by the top and bottom, which will give us 2 square root of 5 over 5. And you'll notice the pattern here. What ends up happening with square root of 5 and square root of 5 is whatever's in this radical comes out by itself. So you end up learning that little trick or seeing that pattern. But those shouldn't be too bad either. The only weird part is, like I said, when you get a radical on the bottom, it's kind of weird. And they didn't actually give us a triangle. They just gave us what cosine is. But you can use your trig functions to make your own triangle and get your adjacent, hypotenuse, or opposite hypotenuse, or whatever leg you want, or hypotenuse, you can do that. So lastly, we've got our trig ratios of special angles. So these are things that you end up just learning. And a lot of these are actually pretty much the reason we do this is because you can actually kind of memorize these. But we'll work through all of them just so you can see them. So if I know that I'm looking for the sine of a 45-degree angle, that means I can look at this 45, 45, 90 triangle, and I can go ahead and do and figure this out, because either way, even if I look at this one or this one, I'm still going to deal with the same numbers. I'll look at this one. Sine is opposite over hypotenuse. So if I have the opposite here, we know that this is x. Even if we were looking at adjacent, we know that both of those are x. And then this is going to be x square root of 2. So if I'm looking at this, I can do this because I can just say opposite is x over x square root of 2. Now all I've got to do is rationalize this because I can't have a square root on the bottom. So that's the only part of this that gets weird. But actually, before you do that, you can go ahead and say, I know that these two can mark out. So what I'm actually left with is 1 over the square root of 2. And then I'm going to get rid of that. I'm going to get rid of that square root of 2 on the bottom by multiplying the square root of 2 on the top and bottom. So I'll end up with the square root of 2 over 2. So that is the sine of a 45-degree angle. So if you ever seen sine 45 degrees, you can already memorize that it's always going to be radical 2 over 2. Now we can go to our 30, 60, 90 and do pretty much the same thing. So if we know we're working with a 30, 60, 90 triangle, we know that our shorter leg, which is the one adjacent to 60 degrees, is x. Our longer leg, which is adjacent to 30 degrees, is going to be x radical 3. And then we know our hypotenuse, which is opposite of the right triangle or the right angle, is 2x. So if we're looking for sine 30, we're saying the opposite of this 30-degree angle, which is x, over the hypotenuse, which is 2x. So now this one's a little bit easier. All we have to do here is cancel out x, and we're left with 1 over 2. So if you ever see sine of 30 degrees, every time it's 1 over 2. Then we can do the same thing with 60, except the only thing that changes with 60 here is that we're going opposite of 60, so that would be x radical 3 over the hypotenuse, which is 2x. So now we can still just cross out x, so we'll be left with radical 3 over 2. And then if we wanted to look for like cosecant 60, we would say 2 over radical 3, and then we'd have to rationalize it. We could do those too. Right now we're just going to look at sine, cosine, and tangent. So we can actually do all of these the same way. I'll work through them real quick just so you can see them. But we can do it even if it's sine, cosine, whatever. We can use SOHCAHTOA and we can do the same thing. So if we go to, let's see, if we go to cosine of 45 degrees, that means we're looking at a 45, 45, 90 triangle. So cosine says do adjacent over hypotenuse, which is still just going to be the same exact values. So it's going to be x over x radical 2, which is going to give us radical 2 over 2, as we saw from doing this one. It's the exact same. So anytime you see sine 45 or cosine 45, it's radical 2 over 2 every time. Now, when we look at cosine of 30, we're looking at this 30, 60, 90 triangle. And if we look at cosine of 30, we're going to go adjacent to that, which is x radical 3 over hypotenuse, which is 2x. And that's actually the same thing as sine 60. So those pretty much just flip. So that's going to be square root of 3 over 2. So anytime you see cosine of 30, it's always going to be radical 3 over 2. Cosine of 60 is just the same thing as sine of 30, but I'll show you just so you believe me. So if we look at sine of 60 and or cosine of 60, we're saying the adjacent, which is x, over the hypotenuse, which is 2x. So x over 2x, then our x's cancel out and we'll get 1 over 2. All right, and then last we've got tangent. So if we had tangent of 45 degrees, we're saying the adjacent over the hypotenuse. So it doesn't matter which 45-degree angle we look at. Pretty much we're saying our legs, one of our legs over the other legs, and both of our legs are x. So that's just saying x over x. And anything divided by itself is just 1. So tangent of 45 degrees is always 1. So if you see any time you're on the ACT or anything like that, you see tangent 45 degrees, it means that, or you can already say that that's 1. Now, tangent 30 is a little bit different. So if we're saying tangent of 30, we're saying the opposite of that, which is x. So x over the adjacent, which the adjacent, or the leg adjacent to 30 degrees would be x square root of 3. So now we're going to have a problem here because we can cancel out x and x, which we're left with 1 over square root of 3. But now we have to rationalize that. So we can do it. It just means that we take square root of 3 over square root of 3. We multiply it by the top and the bottom, and we're left with, let's see, we'd be left with square root of 3 over 3. Because square root of 3 times square root of 3 is square root of 9, and square root of 9 is 3. So tangent 30 is equal to the square root 3 over 3, or radical 3 over 3. So if you ever see tangent 30, immediately it's radical 3 over 3. And then tangent of 60 degrees is the same thing, except they're flip-flop. So now the opposite is, now the opposite of our 60-degree angle is x radical 3. So we'll say x radical 3 over our adjacent to 60 degrees, which is x. So now our x's just cancel out, and we're left with square root of 3. So anytime you see tangent 60 degrees, it is square root of 3. So some of your homework problems will actually be coming from these. And the reason that you'll see these again is to try to help you start naturally or organically memorizing these, because they're good to know. Because once you get on like ACT and stuff, they'll throw little stuff like this at you, and they'll see, basically the ones who have it memorized will be able to crank it out super fast. But that's going to be it for this video. I know it's really long, so I'm sorry, but that's going to be it for this video. We'll go over more of this stuff in class, but make sure you get all of this written down, and then we'll probably go over some homework too.